Today I'm going to talk about text categorization. I'm going to talk about two approaches. One is the categorical distribution approach, and then it's the second one is the logistic regression approach. And the outline of this presentation is first I'm going to talk about the categorical distribution that is based on Bayes theorems. Then I'm going to model directly the posterior, and this allows to see that the key component of these two approaches is the text representation, and then we are going to assume or to develop the general case for this problem. Now, let's talk about Bayes theorem. The beauty about Bayes theorem is that we can model the probability of the class given the input x by only focusing on the likelihood, which is this term. This is the likelihood which model given the class we are going to model the input. And what we can do is that we can assume that the inputs are taken from a categorical distribution with the parameters p, but these parameters are not in general for all the data set, but are only are with respect to the class C. So what I meant is that we are going to take from our data set T, what we are going to take is only those elements that has the class C. And we are going to call that our set DC, which is the data set containing only the elements that have the class C. With that, we can use this DC set to estimate the parameters PC. In order to do that, what we can do is maximize the likelihood estimator. So the maximum likelihood estimator is a function of the parameters, and we are going to make the partial derivative of the parameters that we are interested in, which is one of the parameters of the whole distribution. And the idea of the maximum likelihood estimator is to find the parameters that maximize the probability of seeing all the elements in the set DC. So that's what we are maximizing, where this f is the probability mass function of the categorical distribution. Given that we are modeling as a categorical distribution, the probability mass function of the categorical distribution is this term. This is the probability. Now, this x is a text, and what we can assume that all the words in the text are independent, and if all the words in the text are independent, then the probability of seeing the joint distribution of the text is equal to the product of the individual probabilities of just seeing one word. So this second product is because we are assuming independence. Then we can substitute, this is the probability mass function, we can substitute the probability mass function, and what we obtain is this equation, which is the equation that we want to maximize. Now we can work on that. We equal this one to 0, we solve for it, and then we will find a closed form, an analytical form for the parameters, for the value of the parameters, for all the parameters, which is just, the result is very simple, which is the frequency, the normalized frequency for each word. That's the value of the PC. So we have the different words, and then for each word, the value that has in that place is the normalized frequency of the word. Now, let me talk more, not about how we can estimate the parameters, but let me talk more about how once we have the parameters, what can we do with the parameters. So let me talk about the prediction. The likelihood is proportional. It's not the likelihood that it is proportional, but the posterior is proportional to this equation, to this part. Taking the log of the posterior, this is the posterior, so we have a text that is composed by L different different words or L different tokens by L tokens. So the length of the text, the length of the sentence is it has L tokens, and then with that, given this text, what we can predict, what we can estimate is the probability that it belongs to a particular class. And this is proportional, meaning proportional is that we take away the normalization factor in the Bayes theorem, is proportional to this term. And as you can see, here is the prior, the log prior, and here is the log of the likelihood, and the sum goes for all the words in the sentence, and it goes to L. We can see that, imagine that we have individual words, then what we can see here is that from our parameter P, from our parameter P that it's a vector, or can be represented as a vector with a vector with dimensions d, meaning that d is the size of the vocabulary. We can see that we are only focusing on the elements of that vector that has a token associated to it. So if nothing is repeated, then we are only assuming that it's the value. So we are only assuming of all the different values that are associated to each, of all the different values that are associated to each word in L. If there are repetitions, so if two words are repeated, then what we are seeing is that we have, if they are repeated twice, that we have 2 times the probability of the token repeated. So my point is that we can make, instead of going for all the words in the sentence, for the L different tokens in the sentence, we can codify this and go for all the different words in the vocabulary. We can count, and we can create a function that is going to be the frequency of the I token in the text X. If the I token is not in the text, then the frequency of that token in the text is 0. If the I token in the text X is repeated twice, then the frequency of that one is 2, and so on. And then the parameter P we already know because we estimated, we have the values for that parameter. So as you can see, this part, it's just a way of doing the dot product. So the dot product of two vectors. Which are the two vectors? Of course, these are not represented as vector. Well, one vector is this one, and the other one is this one. So we can use this fact to remove this summation and to represent that. So here we have one vector, which is the vector of the parameters. Here we have another vector, which is the output of codifying the text as the frequency of each one of the tokens in that text. And well, the prior is still the prior. It is, but remember that the prior here is another number, so it is a constant. Now, in order to move on or to continue with this definition, what we are going to do is we're going to name this vector frequency and this one with a different notation, because that it will help us to understand what the other formulation. So we're going to say that the frequency is a function that is transforming a text into a vector, the vector of frequency. So we're going to assume, we're going to call it the function m. M is a function that receives a text and returns a vector. In this case, in the case of the that we are using the Bayes theorem, it is the frequency Bayes theorem, and the inputs are distributed as categorical. Then the m is the frequency. Then this other vector we are going to call it, given that it is a vector of probabilities, but in fact we can assume that it is a vector of just weights. We are going to assume that we have a vector of weights W, and they are dependent of the class K. And this, the prior is just another, it's a constant, so we are going to assume that it is a constant 0. This is the likelihood. With this notation, what we have is the log posterior is proportional to this equation, and as you can see here, that equation is just a linear equation. So when we are modeling using Bayes' theorem, and we are assuming that the inputs are distributed as a categorical distribution, then what we are in fact doing is that we are assuming that the model is linear, and the weights we estimated, so the weights are the parameters of the categorical distribution, and m is the frequency. Now, if we take the logarithm, then the probability of this one, the probability of giving the input x, the probability of the class y that belongs to one of the particular classes given the xy, well, is proportional to the exponent of the linear equation. And well, it is proportional, but as you know, or you can imagine that if we sum for all the different k functions, so if we have the sum for all the different k and we divide this one by that term, then it is the full probability, so it is not proportional. So we just need to add to this term a normalization factor, and we transform this value to a probability. Now, let's move on to the posterior. And the posterior, what we are going to do with the posterior is that we're still going to use the categorical, but then we are going to use it in a different way. Instead of using for the categorical, instead of using it for modeling the inputs, for modeling the input and for modeling the likelihood, what we are going to use is model the posterior as a categorical distribution. So where the posterior is this one. So what we are going to assume is that the class is distributed as a categorical distribution, but the parameter of that categorical distribution is going to be a function of x. That function of x, so the parameter b in the categorical distribution, is being taken by the function f, and if it is taken by the function f, then the function f must have the same characteristic of the parameter, which is the function f must return a vector in a k-dimensional space, because we have k different classes, and the sum for all the functions, the sum for all the elements in the vector, all the components in the vector, must sum to 1. Now we can follow the same approach. We can use the maximum likelihood estimator to estimate the parameters. Now we need to estimate the parameters of the function f. Using the maximum, we can use the maximum likelihood estimation, which is now the data set we are going to use the full data set, and this is the probability mass function of the categorical distribution. So this is the probability mass function of any categorical distribution. We can use probability, we can replace the probability mass function here, and then the function that we need to maximize is this one. This is the maximum likelihood estimator. Instead of here is the function that we haven't talked about it, but we need to estimate the parameters of that function. Is if instead of maximizing the likelihood estimator, we minimize the log likelihood, so we just make the negative of that function. What we have is that this term is known as the cross entropy. This term is the cross entropy. So maximizing the log likelihood or minimizing the negative log likelihood are equivalent, and by minimizing the log likelihood, what we are minimizing in fact is the cross entropy. Now, we need to have a way to comply with this restriction, and one way to comply with this restriction is to develop to use any function w, that this function w is going to be, we are going to use another function, any function h, and this function h is going to use another function inside w, which this function is the one that is going to be using the parameters. To comply with the restriction, we only need to have a normalization factor, and we can use the same idea that we saw on Bayes' theorem as the normalization factor. So we just need to sum for all the different functions h for all the different classes, and then what we have is an f that complies with this with this restriction. We can work with that equation. We can make the substitutions and do the derivation of the equation, but in order to move on to have a better a solution, what we need is also to have an idea about what is h. So what we can assume, or we can decide, it's more appropriate to say that we are going to decide that h is the exponent. And if it is exponent, then f turns out to be this expression, and this expression is known as softmax. Using this fact, what we end up is with this result, which is quite easy, which is a simple equation that is still dependent on the function w and the partial derivative with respect to the parameter w. Y is we still have this term. That we need to talk about more, but here we can see that the first part is the prediction. So once we have the parameters, this is the prediction, and this is the true class. So here we have the difference between the prediction and the true class, and we need to assume something about this one. We need to assume something about that one. So we can set w to whatever we wanted to set it. So w can be any function, but in the multinomial logistic regression, w is a linear equation. A linear equation means that we have parameters, we have a vector of parameters, we have the input x, which is a vector, and we have the bias term. And so in the multinomial case, this is the form of w. If we make this substitution, then if we make this, so if we replace this w with this, still we cannot find an analytical solution for this one, and so we need to rely on optimization method to obtain the parameters w. But before we move on, let us focus on this one. So this is a linear equation. In the multinomial case, we are assuming that we have a linear equation. And look at this one, and let me go back a few slides to show you the way that we represented the model when we are assuming that when we are using Bayes' theorem. Look, here is also a linear case. We have parameters w. We have a function that transforms x into m is the frequency, but what it is m doing is transforming the text into a vector, and we have the bias. So these two formulations are equivalent, but in one, w, in this one, in the multinomial logistic regression, w needs to be obtained by using this equation in an optimization algorithm. That's the difference between the two approaches. This is more general, and because it's more general, because also we have this function that could be anything, but even if we assume that it's the linear case, the difference is that w is the way that we are estimating w, the parameters w. Now, let us assume that w is already estimated. So in the case of the prediction, we have the following, which is this is the posterior, and what we are predicting is just putting everything into place. We are making a linear equation here to make the prediction, and this is just a normalization factor, and doing this x, I'm going to replace this x because x is a vector. So what I'm going to do is I'm going to put it into the words of the approach we did with the base theorem. That is that we are going to have a function m that transform x into a vector. So this one, instead of using x as a vector, we are using the function m, and we are going to assume that m is a function that transforms the text into a vector into the vector space of dimension d. In the case, for example, m, one particular function that we already know how to use is the word frequency. So m, we can use the same m that we use in the base case. And that kind of allows, now with this equation, as we can see, these w's are estimated. This function is any function that has this signature. In the case, we have seen one of them, which is the word frequency, but m can be anything. If we are expressing this one, if we are expressing this this equation using m can be anything. The only restriction is it receives a text, and it needs to give us a vector in a d-dimensional space. So, and the parameters w are estimated using an optimization algorithm and solving. Basically, the optimization algorithm is using this rule to optimize the parameters. Now, what we can do is, well, now that we are here, now we can see that there is a relationship between the first approach, the categorical, when we assume that when we use the base theorem, we assume that the inputs are categorically distributed. There is clearly these two approaches are a linear equation. Turns out to be both of them linear equations, where the only difference is the way that the parameters w are estimated, and the other difference is that in the case of the base theorem, m is the frequency and it is fixed, but in the case of the multinomial logistic regression and in the logistic regression general case, and the logistic regression, m is just a function with this signature. So we can use the fact that m is just a function, and then we can start talking about the different ways that we can represent m. One particular way that another particular function that has been used as an m, as a text transformation, it is TF. It is what it is known as term frequency inverse document frequency. And the term frequency inverse document frequency, well, the first part, it is defined like this one. So the first, you have a product of two things. The first one is the term frequency, and the second one is the inverse document frequency. The term frequency depends on the x, and the inverse document frequency depends on the data set, on the whole data set, the training data set. The term frequency, we know what is the term frequency, because the term frequency is in fact, we have been calling it frequency, is what we have been using on to compute what it is our definition of m, the previous approach. But now another way of using the term frequency, instead of using 1, 2, and 3, 4, which is the frequency, we can use the normalized version of it. So we have an input, we can normalize it. So we have a text, we go for all the tokens in the text, and the term frequency of the element I is, well, we count how many times we see the word index by index, that the word that belongs to the index I, we count how many times we see that word, and we divide it by the number of words in the text. So that's the normalized version of the term frequency. And what we haven't seen is the inverse document frequency. And the inverse document frequency is just the number of times we have seen each token in all the documents in our collection. So and it's the inverse of that. And in order to keep the numbers more or less equal, then normally is being used the logarithm of the inverse document frequency, and what it's doing is the following. So the inverse document frequency of the word of the token I is just the number of times, this one is the number of times that I can be seen in X, and X goes for all the elements in D, and this is divided by N. Of course, this is by the number of different documents that we have. Documents here is the data set that we have, and this is the way that the inverse document frequency works. And of course, we can implement different ways. We can develop different text transformations of different functions M that are going to receive a text and returns a vector. Now, the general case is the following. So if we are not interested in the probability of the class, if we are just interested in the class of a particular input, in the class of a particular text, then the class is just the maximum argument of all the classes given the output of the model, and we don't need the exponents, because the exponents are not going to change where the maximum is, and we don't need in our formulation the normalization factor, because the normalization factor is not going to change where the maximum value is. So we only need the parameters W. We only need the text transformation, and of course the bias term, which is the other parameter. Now, if for example, if we assume that X, if we assume that we transform the text using the text transformation, and then we have the vector X, both face to represent the vector, then what we can see here is that this is a function G. So we can keep the class, and we can define that we have a function that we have k different functions G. All of them have this form, and so we are somehow encoding this idea, but we are abstracting ourselves on the fact that it is a linear equation, and we are going to call it G. So the class of any input X that it's already been transformed into the vector space is just the argmax, so the maximum argument of all the different functions G that we are using to model. And this is the general case, because we can see here that we have a free form of G, so that G can be anything, and it only requires to work on a vector space, and we only need to develop k different G's. So if we have k classes, we have k different G's, and then we can solve this problem. Now, for the base case, we're using the base theorem. M is the frequency, W is this one, and we know how to estimate this one, and the bias is the prior. And for the multinomial case, M is a function that lives in a d-dimensional space. M is a text transformation. It's open. We can use whatever we want. W is a parameter in a d-dimensional space, and where W we estimate it using by minimizing the cross entropy, and also this is just a bias term that is also optimized that it is also optimized by minimizing the cross entropy. Now, with this, we finish the talk about text categorization. But before we finish, let me just point out where all these components are in the notes. So, in the notes, all these components, the first part, when we assume the categorical case, the categorical case is in text categorization. It is in here, so we are assuming the text categorization approach that we are the problem of text categorization. We are assuming that the inputs come from a categorical distribution, and we use Bayes' theorem. Now, where is the other approach? The other approach is here, back of our models, and well, here are the definition, here how we can solve this one, but this is the final output. The final output is that we have a function m that transforms the text, and the text and how are we going to implement this one? Well, the way that we are going to implement this one is pretty easy, because we are going to use a lot of functions that has already been implemented. So this is the way that we optimize the different the parameters w. But now the term frequency, so the frequency of the word, the way that we are going to estimate it is using one of the model. Is using the text model. So we have seen this one in order when we were tokenizing. The part that we haven't seen is this parameter. This parameter is telling this class that we are going to. This class is called text model, but it is a text transformation function that is going to transform a text into a vector space, and the method that it's going to use is, if you have TF, it means that it is the term frequency. You need to fit it, so you need to estimate some parameters, and what you are going to do is you are going to use the dataset to estimate those parameters. It's easier to understand once we have this class, then we can use it, and by using it we can see that what it is doing, this method is transforming the text into the text into a vector space. So for example, the dataset that we are using is in Spanish, but it doesn't matter. We are going to transform this text, which is good morning, morning, into the vector space. There are two words. The first one, good, and the second one, day, and morning, and the second one, well, it's not morning, but this is good morning, and the second one. So there are two words. One of them is repeated twice, so we can see that the vector is a vector of full with zeros. We are using a sparse representation of the vector, where this component, the component 263, represents buenos, or good, and it is a normalized frequency, as we saw in the slides, so 1/3. And the second word that is repeated twice corresponds to the index 87, and well, this is 2/3. Now, well, that's the term frequency. Once we have the term frequency, there is another method that allows to transform a list of text. So instead of giving one text, we can give a list of text, and this one well, returns a matrix, a sparse matrix. So we can see that the sparse matrix is that it has one row, which is the sentence, and it lives in 3291 dimension. We can, once we have the transformation, then we can use the multinomial logistic regression to solve this problem. And what we are going to use is as a scaffold in order to measure the performance. But let me show you where is the transformation. So the transformation, so here it's the transformation M. Here is transforming all the inputs into a matrix, and then the multinomial logistic regression, it is trained here. So the parameters of the multinomial logistic regression are estimated by this line of code. Here we are saying that the type of algorithm that we want to train is a multinomial one. Once we train them, once we estimate the parameters, what we can do is we can use it to predict. But before we predict it, what the first step is we need to transform the text into a vector space, and then we use it to predict, and pretty much that solves. So everything that we have seen is we have seen the mathematical tools that allows you to implement this class as a logistic regression, as a multinomial logistic regression, but during class we are going to use some libraries that are already implemented. And the function m that I have been talking about, well, is a function that is being used in this part. And the first part is that we need to estimate the parameters of that one, and this is done here. The parameters of the distribution are this one. Now, with that, you can see the performance of that. The same code can be used with another text transformation, for example, term frequency inverse document frequency, which is this one. And the only difference between the two of them is that the term frequency inverse document frequencies is also implemented in this class, but it is the default parameter. So if you don't give anything, then if you don't give any argument, then what you are doing is term frequency inverse document frequency. The same example, but it is not repeated the word twice, so it's just repeated one. But the index allow you to see that the weights of this component 263. Let me go to 263, which is buenos. So you can see that the weight of the first component is different in the two formulations, and that's the idea of the text representation. So each word is going to be weighted by a different value. Now the code, the second part of the code remains exactly the same. So you can check, you can review it, and you are going to see that it is the same code. And then the performance, it's a little bit different. The performance is this one, and you can compare the performance of the two text representation, and they are a little bit different. We are going to be working more about this one, and well, in order to finish this, just let me show you the word cloud of the text of the weights for all a word cloud of some tokens. One of them weighted using term frequency inverse document frequency, and here is the word cloud. As you can see, the words are uncommon words. This is what term frequency inverse document frequency, so they are weighting more heavy the words that are somehow unknown, and the word cloud of the term frequency is this one. And as you could imagine, that the words that the term frequency are weighting more are the values that are higher are the most common words, and you can see here that and so on. Well, with this, finish the part of text categorization, and in particular finish the part of barcode models, and how these two algorithms are kind of a linear way of modeling. It's a linear solution for text categorization.